So it's my pleasure to introduce Mark Paris, who's a staff scientist at Los Alamos National Lab. And Mark's a little different from a lot of his focus, research focus, than a lot of the speakers we've had here, since he really comes from theoretical nuclear physics side of things.
Complete imposter.
Nuclear reaction side of things, which is, what's that?
I'm a complete imposter. I shouldn't be at an astrophysics
No, it's
summer
like
school.
all of us.
Okay, well, thanks very much to you, George, for inviting me to give a couple of lectures here at this distinguished summer school. And I'd like to thank the organizers of the conference, in particular Sue, Billy Kay, and Dana for all their hard work. And also in particular Evan Groves for preparing a lot of the materials that we'll be using for the workshops this afternoon and tomorrow afternoon. So you should have, if you haven't got one, hold up your hand and we'll get you one. A few pages that will guide you through this afternoon's workshop, which we are going to be, the ultimate goal of the 2 days is to make what we've started calling the Schramm plot of primordial light element abundances versus baryon number or baryon ratio with respect to photons. So here's the organization of the course. We'll have lectures today and tomorrow. Wow, the light stuff doesn't come out. Wow, okay. Which will be an overview of cosmology. For today, you shouldn't be looking for too much by way of groundbreaking research. A lot of it will be context for what we're going to do in the workshop this afternoon and for what comes tomorrow regarding nuclear reactions. I'll do a little bit of kinetic theory and then introduce the topic of Big Bang nucleosynthesis so that you can self-guide yourself through the workshop this afternoon. Tomorrow we'll talk about scattering and reactions and a little bit about neutrino energy transport and its effect and impact on Big Bang nucleosynthesis. Today's workshop is, there's an exercise to compute the abundances of the 4 lightest elements, deuterium, the 3 nucleon nuclides, and helium-4 in nuclear statistical equilibrium, and then to compute the electron fraction, assuming charge conservation. And then tomorrow we'll make this Schramm plot, which is the primordial abundances versus baryon number. I plan to put lecture notes on the web, and I'll let you know what the URL is for that. So in preparing these lectures, I used a lot of resources, and here I've listed a few of them that I found particularly useful. I won't go through them, but if you've never looked at this little book by Jeremy Bernstein, Kinetic Theory in the Expanding Universe, particularly nice reference. Okay, so here's the outline for the lectures today and tomorrow. I already said that we'll do basically overview today. I'll spend a lot of time actually on general relativity and the cosmological dynamics that come from it. We'll talk about Big Bang nucleosynthesis in the context of the Boltzmann equation. We'll derive the Boltzmann equation in both flat and curved space-time. And then tomorrow I'll tell you what we're going to talk about at that point. Okay, so let's put BBN in context. So Big Bang nucleosynthesis is the formation of the lightest nuclides in the primordial fireball of the Big Bang. So we're talking about deuterium, triton, helium-3. Helium-4 is out on its own because obviously it's the biggest guy in town, has the largest binding energy per nucleon of the light elements that we'll be discussing, and it dominates the scene pretty much exclusively. So let's think about the evolution of the early universe in terms of what's happening, the epochs. And so I'm imagining as we go from early times when the universe is hot and dense to when it's cool and rarefied, you have these various labels for these epochs. So at very early times, 10 to the minus 50 or something seconds, we're in the Planck era when we expect that quantum gravity should be important. Of course, theory still forthcoming on that. Stay tuned. After that is the granulification scale and inflation, electroweak phase transition, quark-hadron transition, which we don't even know if it's a phase transition or not, and then BBN, recombination, galactic formation, and large-scale structure. So we're focused on this particular epoch. The time of BBN is about a second to about 100 seconds. That's where we are here. So this is a plot that I've stolen from lectures by Boltzmann, which are referenced on that one of those first slides. And so there's the inflation epoch. In between inflation and BBN, there's weak decoupling or neutrino decoupling, and then recombination, et cetera. So BBN ends here on this plot at about 3 minutes. I'm not really sure if that's rigorously true. It could go on a little longer, a little shorter. But the temperature scale it's actually a little less than an MeV, say 1/10 of an MeV, and then down to few keV. And just to blow up that BBN epoch a little bit, another obviously image I stole from the web. This is baryogenesis down here, and then where nuclear fusion begins, that's what I'm calling the beginning of light element formation. So you build up from deuterium to the 3 nucleon nuclides up through lithium and beryllium-7, and that process ends here according to this. All of our information, of course, well, a lot of the information we have about the early universe comes from the cosmic microwave background radiation, and that happens much later. So you can ask questions about, is it important that there's this time gap between the end of BBN and recombination, but we'll just leave that aside for now. Okay, so returning to the context, there's a lot of very interesting physics that go into the BBN epoch. The universe should be viewed as a cooling thermonuclear reactor during this part of its evolution. And that's because the work of the expansion of radiation against whatever, space-time, cools the radiation and matter. You have an interplay between weak and strong nuclear interactions that can be very rich and complicated. And then, of course, you have to consider Boltzmann transport of energy and momentum. Not really, as you'll see, because everything interesting happens during these epochs of non-equilibrium phenomena. So just to put 5 decades into 2 lines, there have been some stunning successes with the hot Big Bang model. In particular, the expansion of the universe was predicted and observed. The cosmic microwave background also. And then the relative abundances of helium and deuterium, you'll see that the helium we've measured fairly accurately to the level of a few percent. observed it, I mean. And the predictions are very, very good with it. Deuterium, actually we've measured now, observed to less than that, maybe 1% or 2%, and both of these observations are going to improve within the next decade significantly by possibly an order of magnitude. However, there still remain perplexing anomalies with the lambda CDM called dark matter model. And that is the origin and nature of dark matter and energy, which, as everybody knows, makes up most of the closure density of the universe. And more along my interest is the lithium problem, understanding the nature of why the prediction for lithium-7 is significantly higher than that observed. And so, don't worry, I'm going to explain this in detail. So before I go on, I should say, as George pointed out, I'm a nuclear theorist. I do primarily light nuclear reactions. If you know anything about Los Alamos, you probably know why we're interested in that. BBN gives us a almost orthogonal environment to test some of the nuclear reaction theories that we have. So that's why I have applications in both Los Alamos interests and in fundamental science. Also, I'd like to keep this really informal. Just interrupt freely, say hey yo, and we can have a conversation. If you have had a chance to look through the notes and anything comes up with those, that's game for questions too. So, okay, so here we go. Observationally, how do we know that our predictions for BBN are any good at all? It's because astronomers have done an incredible job looking into the cosmos and telling us what's out there. In fact, very recently, at the end of 2013, Max Bettini, Ryan Cook, and company published a 2% precision primordial deuterium measurement by using the 10-meter telescopes at Keck, excuse me, to look at the damped Lyman alpha forest from a quasar at about 3.1 redshift. And what they did was to knock down the error bar on that to a significant enough level that you can now probe microscopic aspects of nuclear reaction physics with cosmological observations. It's truly an astonishing development, and it's one of the primary reasons that I'm standing here today is we're really trying to sharpen the tool for understanding primordial BBN. So some of the things that make this possible are adaptive optics, which saved the Hubble Space Telescope. You probably know that story. Space and ground-based observatories, and coming up within the next 10 years or so, first light should be had at some of these 30-meter class telescopes. The European Large Telescope, which is pictured here in an artist's conception, or maybe this is the TMT artist conception. Thank you. Also, you guys probably know a lot more than I do about this, but the CMB is being better and better measured, of course. We have recent results from BICEP2, which I haven't put up there for some reason. And then all these other Atacama, South Pole, Polar Bear, all offering better information about earlier times of the universe, in particular inflationary scales, but also has important implications for BBN. Cosmology, as I've said now, is so precise we can check nuclear physics with it. but you can also do tests of physics beyond the standard model. And one of the things that we're very interested in is the fact that you can access certain reactions that you can't do in the lab. And nobody's ever going to take, well, I shouldn't say never, right? It's going to be very difficult to fight the political forces who believe that safety is much more important than any other concern, to do things like triton goes to 2 neutron alpha reactions. I'm just picking one at random, right? So maybe we can use BBN and cosmology to access some of these reactions. Okay, so now let's talk about the theory of general relativity and how you solve it for the case of the universe, where you're assuming homogeneity and isotropy. Robertson and Walker, so the F is Friedman, the L is Lemaitre, RW is Robertson Walker. They basically showed that that if you have homogeneity and isotropy, then the Friedman metric is unique. But it was really Friedman and Lemaitre who, within a few years of each other and independently, wrote down the solution to Einstein's equations for a homogeneous isotropic scenario. And this led to, I just put the Einstein equation, the one of content, in fact, up there, and the metric, but we'll talk about that in much more detail, so I won't mention it right now. But the 3 big observations that come out of this, as I've already said, are the Hubble expansion of the universe, the fact that every point is moving away from every other point, the prediction of the cosmic microwave background, which has a black body spectrum, which has been observed to ridiculously high accuracy. In fact, deviations from it, which give us most of the information about structure in the universe, are at the level of 1 part in 10 to the 6. Is that right? Or 10 to the 5? Anyway, pretty close. And then once you have this homogeneous isotropic flat universe, that's what HIF means over there, then you're pretty much stuck. You can't do anything else with space-time. All of your tuning has to happen on the right-hand side of the equation in the energy momentum tensor, the time-time components. So Einstein, Friedman came up with, Einstein came up with the equations. He didn't like the fact that the universe was dynamic, so we put in the cosmological constant. Friedman said, no, it's fine. The universe is probably evolving. And Friedman was, of course, correct. If you look at the corrected observed luminosity versus the redshift, you see that largely the Hubble expansion is observed by these very bright galaxies that are plotted on this figure. This figure is from chapter 14, I think, of Weinberg. And if you needed any more evidence of the enduring legacy of the Einstein-Friedman equations, you might look at this fellow's inked up torso, where he has put the Einstein equations. Yeah, anybody who's been inked knows how painful this must have been, right? I don't have any, but I've heard it's awful. This is not me, by the way. No, he's got a much denser beard.
It's actually not true that I force my students to get that.
Sure, Josh. Well, I don't know if this guy ended up in research physics, but certainly he took seriously his instructor's admonitions to show his work, right? I mean, he's got the curvature scalar here expanded out in all of its components, kind of not necessary. Anyway, Evan and I checked. I mean, it could have saved a lot of pain, right? The other thing is, who did this? Who actually sat there and did this? Anyway, okay, maybe it's disturbing. I should probably change the slide. But we went through.
Yeah, it's really pretty fun.
Yeah, it's done well, and there are no mistakes that I detected. So, okay, so let's derive these really quickly. So Einstein arrives at his equation by enforcing things like matter, energy momentum conservation. The Bianchi identity enforces that on the Einstein tensor. Unfortunately, I won't go through the derivation of this equation. We'll just take it as a given. On the right-hand side is the energy momentum tensor, which is given for ideal fluids, so no viscosity by the right-hand side. P is the pressure, rho is the energy density, and then I've listed out here basically the equations on our friend's torso in terms of the Einstein tensor, in terms of the Ricci tensor, and the curvature scalar. The Ricci and curvature are given in terms of the Riemann tensor, which is given as derivatives with respect to the affine connection. I've written out the components of the affine connection here. You can see that basically everything is zero, except for the time, space, space, and space, space, time component, and then the spatial, all spatial components. In the curvature zero case, so that's the one we'll primarily be working with because observation tells us that it looks like the universe is spatially flat. This is zero as well. Where does the metric come from? Well, the time component should be a constant because remember we're going to assume that matter and energy are spread out over the universe at very large scale. So there's no way that you can have gravitational redshift, for example, due to matter or energy locally. You only get that due to expansion of the universe. And then the time dependence in the spatial part comes from the fact that non-trivial solutions of the Einstein equation require you to have some time dependence somewhere. So when you plug those components of the affine connection into, oh, by the way, this is an exercise in the notes, and I'll give you that URL tomorrow, hopefully. You get these two equations, which are conventionally called the Friedmann equations or the Einstein-Friedmann equations. We'll talk about solutions of these in a slide or two. Like I said, you have covariantly conserved energy momentum, and then if you look at this setup, you have two equations. I should say that the covariant conservation of the energy momentum is already built into these two equations, which I haven't used yet. And that's because of the Bianchi identity in the Einstein tensor. In other words, if you differentiate this equation, you get a constraint, which is this. And that's the same thing as what's in the energy momentum equation. So at this stage, I have two equations for three unknowns. That means I need to assume one more, and that's the equation of state, which relates the pressure to the energy density. So let's look at the classes of solutions that happen for this metric. This is the spatial curvature K. You can see these three curves correspond to, it's a trichotometric constant, which means it can only take on three values, +1, -1, or 0. -1 is the de Sitter universe, so sort of like a saddle. It's got negative spatial curvature. K equals +1 is closed universe. That means that the eventual state of the universe is to go back to a singularity, if you believe classical general relativity, all the way back to the future. Here we're somewhere in this point of the evolution where the curvature, of course, is negative, but everything is moving away from everything else. The universe is getting larger, things are getting red-shifted. Once you get to this point, things become blue-shifted. So the light of distant galaxies would then be at a higher frequency than it was emitted at. The borderline case, k equals 0, is actually the one we think obtains now, given the results of studies by Perlmutter and Rees and others on studying the motions of distant supernovae. Okay, so I won't go too much into detail anymore on this figure, but all of the quantities here should be more or less familiar to you. The current critical density, which is given, so the Hubble constant is the value of the Hubble parameter today at t0. So set k equal to 0, and then ask what is the critical density that you need to have a flat space-time. And it turns out that if it were all in matter, that you would find about 5 protons per cubic meter out there. Of course, this is much, much larger than the baryonic density that we see now. So given the fact that we think k is 0, the closure density must be coming from other sources than observable baryonic. One last thing that really simplifies our task when we're talking about early universe physics is the fact that the space-like hypersurfaces of the universe are maximally symmetric subspaces. That means that you can have the most killing vector fields that are linearly dependent of each other, which is given by n times n plus 1, the number of components of a symmetric tensor of n dimensions. So you should think of n being 3 in this equation. It's a direct consequence of the homogeneity and isotropy of the universe. And basically, what it means is that if you draw out the killing vector fields on the space-time and you draw the lines of flow along those vector fields, then those flows generate isometries of the manifold, which means that you move from point to point. As you move from point to point, you don't change the metric. And this is very important because, I mean, if all of that was gobbledygook to you, don't worry. The consequence is here, and this is what's important. First, scalar fields have to be constant. Vector fields can only have time-like components, and rank 2 tensors can only be proportional via a constant to the metric. Okay, if you have these 3 things, you could solve the problem. I mean, that's really what makes this such a useful field of study, is that the metric simplifies our job for doing transport, because transport is very difficult. Okay, so let's talk about the lithium anomaly. So in the figure, what we've shown is, I've stolen this from the review of particle properties, probably familiar to you. Apologize that it's not rendering nice. It looks really nice on my screen. In the top panel is the primordial mass abundance relative to hydrogen of helium-4. The curve is the prediction as a function of baryons to photon ratio, which you can see, I guess you can't see here, times 10 to the 10. So this is a really tiny number, 1 part in 20 billion roughly, baryons to photons. And then up here is helium. The larger box is statistical and systematic at, I think, at 2 sigma, and then the smaller box is 1 sigma, and then those curves are reproduced for deuterium over hydrogen in number, relative number, helium-3, and then lithium-7. So let's go to helium, which is very good agreement. So even for the smaller statistical and systematic errors, the curve goes basically right through the box. the box being determined by the intersection of the primordial component of helium-4 and the baryon to photon ratio given by, let's use the smaller box here, which is the CMB determination of the baryon to photon ratio, or the baryon density. Evan likes to use the baryon density because that's what all the cool people are doing now. Sorry.
That's the CMB. I just
Right,
thought whoever's
right,
involved.
right. Planck does it, so and they are very cool people. And then here's deuterium. There is no observation for helium-3 because it gets processed in stars right quick. But lithium-7, you can see that there's a discord between where we think it should be, which is basically right here, 5 times 10 to the minus 9 with respect to hydrogen, and here, which is observed in very old stars that don't have a lot of metallic contamination. So I mentioned this deuterium observation by Patini and Cook. That's not what's shown here. The Patini and Cook measurement is smaller, and I'll actually show you that in a couple slides. So this is by way of sort of political advertising or whatever. This slide is to show that we're reaching a point in time, as George likes to say, that the observations are getting so good that we'll be setting up an over-determined situation observationally where new beyond standard model neutrino physics likely must show itself. George is very good at putting together words that might seem otherwise to lesser minds at odds with each other. And these measurements are the CMB, come from the CMB, for example, the effective number of relativistic species, so-called N-effective, which we'll talk more about tomorrow, the primordial component of helium. YP is Y primordial, so it's the mass fraction of helium-4. It's not protons. And then the baryon to photon number ratio and the deuterium abundance. So that's why we're spending time on this problem now, is because things are really changing. And you hear a lot about how successful the lambda cold dark model is. I just want to go very quickly and say, that's certainly true. But there are potential cracks in lambda cold dark model, which we should be aware of. For example, if you look at the Hubble expansion parameter, there's a tension between the rates determined by CMB. So this is WMAP9, the most recent complete compilation of that observational program, and Planck within error bars of each other, notably. However, perhaps outside the range of observational measurements, and apparently relativistic energy densities can fix this problem. In other words, ineffective. Another example, I stole this from a talk by Wayne Hugh back in October of last year, is clustering. So I'm not an expert at this at all. Appreciate it if anyone can catch me if I make a mistake. But basically, you're looking at very large and rare dark matter halos about galaxies. And you form this, this quantity called sigma 8, which is the integrated power spectrum over the Bessel function. And if you look at the distribution of these, then the endpoint distribution of where these masses cut off is very sensitive to, for example, the relativistic energy density in the system. And so apparently there's a discrepancy between sigma 8 observed and what you expect by using a fairly sophisticated model that proceeds from the use of the Birkhoff theorem, and should be pretty good. But there is a discrepancy with CMB and gravitational lensing. And then finally, the other crack may be in BBN. Of course, we know about the lithium anomaly. I neglected to say, but it was on the slide, that the deviation is 3 to 5 sigma. But there's also potential discrepancies between the helium abundance and the deuterium abundance. Here's the Patini and Cook measurement that I've been making so much noise about. And here is the BBN prediction done with one of the publicly available codes. I guess, does Planck use parthenopy? So there's a BBN code out there called parthenopy that you can download and use. Although I think I requested it from them and they never sent it.
I thought it was called Parthenope.
Parthenope?
I didn't know it was.
It's a Greek. There's a Greek. It's a Greek name, so I was saying parthenopy, but you might be right. This all has a lot to do with what's happening in the neutrino sector of the physics. There can be thermal effects. If you have more relativistic energy density than you might think from the standard model, in other words, say sterile neutrinos or something like that, then you can have the thermal effects result in, if the universe is hotter later, then weak decoupling will happen later. You'll have less neutrons, and that'll affect significantly things like helium and deuterium abundance. You can also have late decay of heavy particles like sterile neutrinos, which we'll talk about more tomorrow, resulting in less neutrons. So BBN really is becoming a very valuable probe of what's happening in the neutrino sector. You might say, well, maybe the lithium anomaly has nothing to do with nuclear physics or particle physics, physics beyond the standard model. Maybe it's just an astronomical observation problem. The way that you derive, and I think Evan will talk about this a lot more tomorrow, the way you derive the lithium abundance is from this Speed plateau, and that's this from their 78 paper or 82 paper, something like that. And basically what it is you extrapolate the observed lithium abundance to very low metallicity, and you see that it's flat. So you imagine that you've isolated the primordial component because it doesn't depend on which star you're looking at. But unfortunately can't see it on this projection, but there's actually, so this is a recent paper, 2010, that shows that there's a break in the Speed plateau. There's a line here and then another line here. And so the claim is that perhaps this has something to do with the stellar astrophysics. That means you're not getting the lithium abundance correct. So that's possible. Nevertheless, this problem has been raging among stellar astrophysicists for decades. So we're going to proceed with possible nuclear physics explanations and physics beyond the standard model. Even if it turns out that neither nuclear physics or BSM physics has anything to do with the lithium problem, it's still important to do BBN better than we've done it before for the reasons that I've talked about on the last few slides. And then since I'm getting sort of short on time, I'll skip more of the propaganda, other than to mention that one of the things that we want to improve is the description of the nuclear reactions. And you might find it surprising to know that in the nuclear reaction networks, which I'll set up in the next few slides after this one, unitarity, conservation of probability in quantum mechanics, is not being consistently and completely implemented across all of the nuclear reactions that are used for the light nuclei reaction network for BBN. So we're hoping that if we do a better job with the light nuclear reactions, that might have some implication for the lithium anomaly. So we want to incorporate unitarity into the strong and electroweak interactions. And we're also developing new codes, and that's the subject of Evan Groh's thesis, and you should talk to him if you want to get more details about it, because he's very good. Okay, so let's talk about kinetic theory, since that's ultimately where the nuclear reaction network equations come from. We postulate the existence or usefulness, I guess, of the distribution function, which just gives the number density of particles per unit phase space. If you take the stream derivative, you have, basically you're imagining yourself following along with an element of the fluid, so there'll be derivatives with respect to position and momentum. The Boltzmann equation relates the stream derivative to the number of collisions. In the collisionless case, basically since these elements maintain their volume in phase space, the collisionless case means that the stream derivative is 0. All of the changes in the number of particles per unit phase space element happen simply because the fluid is moving in a collisionless fashion. In the collisional Boltzmann equation, there's a possibility to have interactions between the constituents of the fluid knock particles in and out of these elements. And that's given by, so the change in the distribution function as a function of time, simply due to collisions alone, is given by a difference of rate equations in and out, or forward and reverse. And I'm going to go over the next few slides in some detail about what all these things mean. Basically, you calculate from quantum field theory the invariant matrix element. There's some function that tells you about the phase space available initially and finally, so the number density initially and finally, and the Pauli blocking or Bose enhancing factors are in here, and I'll show that in a couple slides, which can also be written as an integral over the cross-section times the relative velocity of the incoming pair. We've used time reversal invariance here to take out the cross-section from each of these factors. Otherwise, if you have time reversal violating interactions, you would have different cross-sections multiplying each of these things. Just to remind you, oh, that's too bad. This is a really nice figure that I stole from my friend. The differential cross-section is, you imagine flux impinging on a target, and you study in your detector at great distance compared to the scale of the target. The number of particles per unit time, if you divide out the initial flux, you get the differential cross-section, so it's an area. Of course, everyone knows that, but just in case it's been a while since you looked at scattering formalism, I wanted to remind you. Okay, so that was kinetic theory in flat space-time. Now in curved space-time, it's basically the same deal. It's only complicated by the fact that the metric is not the Minkowski flat space-time metric. It is the Lemaitre-Robertson-Walker metric, and therefore the geodesics are not simply straight lines, they have curvature. So if you imagine taking the derivative with respect to an affine parameter lambda of the distribution function, which can depend on the 4 position and the 4 momentum of the particle, then you're just going to use chain rule. It turns out that what you end up with is something I've defined here as the Liouville operator. So you see that it's greatly simplified, and this is one of the consequences of having a maximally symmetric subspace that I talked about. So there's a partial derivative with respect to time, so at fixed coordinate positions, and there's a sort of a divergence term that's related to this time derivative of the scale factor. Remember, the scale factor governs how far things are from each other as the universe evolves. So think of just, dynamical change in F versus, sort of proper change due to the fact that the universe is expanding. Just call this Hubble expansion. If you integrate the distribution function with respect to momentum, you get the number density of the universe, which, remember, it's a scalar, so it's got to be only a function of time. And you can write this in terms of the collision integral that I showed on the previous slide. So the collision integral is basically the same. There's this factor of energy that maintains Lorentz covariance. And the Hubble expansion appears in there. You can compactify the left-hand side of this equation to give you the time derivative of the proper number of particles. So this is the number of particles in a proper volume of space-time. So you imagine that the volume that you're looking at is growing with the scale factor, and that the number of particles in there, in the case of the collisionless Boltzmann equation, would be conserved. I'll just mention, because it comes in handy later, that if you have a quantity, let's say entropy, for example, that is covariantly conserved, that means it satisfies this equation, so there's no collision term, and you form the ratio with something that satisfies the Boltzmann equation, then you get rid of this Hubble expansion term. But it's still there in principle. Okay, so let's talk about entropy production, because it's important for the dynamical evolution under the kinetic equations. If you define the entropy current this way, where these are so I'm imagining a single species, this is the distribution function, and you take the covariant derivative, you can show that it has this form, which is always positive. So entropy is, it's positive semi-definite. Entropy is always increasing or zero, never goes down. And the equilibrium case is defined by having this be identically zero. But notice that what this means is that if the collision integral C is zero, proper entropy is constant, and you have necessarily equilibrium distributions. I haven't shown that specifically, but it's true. The collision integral is non-zero. You have proper entropy creation. So anytime you're going through a non-equilibrium situation, entropy is changing, and that necessarily means that the distribution functions are not in equilibrium. H theorem, very powerful. So here's the Fermi-Dirac distribution. Just to remind you, this is the equilibrium distribution for particles antisymmetric under exchange of their quantum coordinates. This is the Bose-Einstein distribution. They both have the limit at very high temperatures of the Maxwell-Boltzmann distribution. Just to remind you what that looks like. Okay, so then, knowing what we know now about the kinetic theory, I want to define three regimes that are important. And we'll probe the kinetic regime in the workshop this afternoon for Big Bang nucleosynthesis. In equilibrium, the rate, which is given by this expression on the right-hand side of the figure, is much larger than the Hubble expansion rate. So that means that both the collision integral and the change in the distribution function with respect to time is much larger than the change in the scale factor. And so you can ignore it. And what that means is that the forward and reverse reaction rates detail balance. And that means that the reaction rate is sufficiently fast so that each particle explores huge amounts of the phase space. And that's the requirement that you need to get to equilibrium. There's a caveat here. It's sort of a technical point because it doesn't matter often in practice. But you should be aware that in the FLRW metric, there is no time-like spatially constant killing field. And that so the killing field generates isometries of the metric. A time-like isometry means that, I'm just sitting here, I'm moving on a time-like curve. As the universe evolves, the metric changes. So there's no way to move along a time-like curve and have the metric be the same. That's all it means. What that turns out to mean is that there are no equilibrium distributions in general in the FLRW metric. Fortunately, deviations from equilibrium are second order small in deviations from the equilibrium distributions. So if you're moving slow enough, you should be okay. And most of the time, I think that's true. There are two cases where there are equilibrium distributions. That's for massless particles and infinitely massive particles. And it just so turns out that that's what we model everything as. So I would call this not a well-probed assumption. So it's something you might think about. So the kinetic regime is where the rate of, let's say, two-to-two body interactions is about the same as the Hubble expansion rate. In that case, that you have the potential for there to be a non-zero net forward minus reverse rate. Boltzmann theorem tells you that entropy is changing. But because of the argument I just gave about second order smallness actually obtains here too, we're going to assume for most of the development of the universe that entropy, proper entropy, is conserved. So that's this assumption of adiabaticity. And then finally, there's the decoupled regime where the rates are so slow that the particles just freely stream through the universe. Their distributions are locked in at the decoupling temperature because they can't be knocked in or out of the phase beta element that they're in. So that's the decoupled regime. So I hope that these are useful concepts for you to structure your thoughts about which various regimes we might be in when we're talking about BBN. This is sort of off the topic just a little bit because it's talking about the evolution from very high temperatures to very low temperatures. BBN is in here along with weak decoupling. Basically what I'm showing here is the effective number of degrees of freedom as a function of time or as temperature gets lower from left to right. So what I'm writing here is the sum over all of the particle species, the photons, neutrinos and antineutrinos of all three flavors, charged leptons, baryons, whatever is out there, sterile neutrinos if they exist, of the energy density per unit volume in momentum space. And so I've written that in terms of the relativistic, so these are all assumed to be of arbitrary mass, but I've written that in terms of the relativistic expression times, so this factor, if mass is 0, then J of 0 is a constant. So this is for, this factor is for massless species. And then you have a correction factor, which is given by this graph at the right, that takes into account the fact that as the temperature in units of whatever the mass of the species is gets higher, then about the time you get to temperature order 1, this function saturates close to its maximum value and then remains basically constant up there. That's basically just you're crossing the threshold to produce those particles. And so as the temperature decreases, you see that the number of degrees of freedom as you go from left to right on this plot is decreasing as well because you can excite less and less things. Here, above the electroweak phase transition, you have everything, right? Gluons, massive vector bosons, neutrinos, everything's playing. By the time you get down here, you're just left with photons, the lightest charged leptons, and the neutrinos, the light neutrinos, all three neutrino species. I just want to point out that you can make a lot of mistakes in making this figure. And the person that I stole it from, Bauman, is very clear about it, so I don't want to make it sound like he doesn't know what's going on. It's just, so what he does to make this figure is he cuts off sort of arbitrarily at 1/6 the mass, because that's somewhere over here. Basically, you've exhausted all of the entropy at that particular degree of freedom by the time the temperature falls below 1/6 of the mass of the particle. And so you just cut it off with a theta function, and you assume everywhere that all of the temperatures are equal to the plasma temperature for the photons. Okay. All right, so this now is particularly relevant for, it says I have 5 minutes on my clock. Is that correct? Okay. So this is how we reduce the Boltzmann equation to the nuclear reaction network, and that's what you're going to use. You're going to be given a code that you're going to have to write a subroutine for in order to calculate the primordial helium abundance and deuterium abundance and everything else. Actually, I think there's, how many nuclides do we have in there? 10? 9 nuclides. So the 9 lightest nuclides in the evolving FLRW metric, it's based on the Kawano-Wagner code. Wagner wrote his paper in 1969. Actually, I think the code is probably even a little older than that. And so basically what happens here is I've assumed for these F factors, which tell you about the relative probability of having 2 of the constituents of this nuclear plasma being on top of each other, just as Maxwell-Boltzmann factors. So I'm assuming that and this is a very good assumption for baryons, that the number density is low enough so that the effects of wave function overlap of the particles is negligible. In that case, you have Maxwell-Boltzmann statistics. And then you can reduce this equation. It's an exercise. If you can do it in detail, then you get a gold star. Because I actually, to be honest, I still have trouble getting from here to here. I know that both of them are right, but maybe one's more right than the other. This one is absolutely right. This one, this is what's in all the textbooks, so I'm not giving you anything hokey. I mean, this is what people say is correct. So what's in here is basically the rate at which the reaction happens, and then this is the sync term. So if you're looking at the abundance of, the number abundance of a particular nuclide labeled by alpha 1, then if that's around and it interacts with species alpha 2, then that takes it out of the phase space element. That's what this negative sign is doing. If you have other reactants that give rise to alpha 1, that's what this guy is doing. So this is a source and this is a sink. And so what you're going to solve with the Kawano-Wagner Groves code, because Evan has significantly massage that code to make it a little bit easier to use, is solving a coupled set of nonlinear first-order differential equations. And I think it'll be fun and useful too. The first exercise that you'll do is just to, what is it?
The first exercise will be to do the NSE.
Oh, right. So the first exercise is NSE, so maybe we should do NSE first. Yeah. So the first exercise is to do nuclear statistical equilibrium, which means that you assume chemical equilibrium between protons, neutrons, and all of the light nuclides up to helium. And then that'll give you these dashed lines, which this, unfortunately, this is temperature versus relative abundance relative to the relative abundance of, what is it?
It's the abundance.
Sorry,
Okay.
it's just
Relative to
the,
hydrogen.
right, great, thank
Right.
you.
So hydrogen is something that is going to be something like 70%.
Right.
Actually higher than that, rather. Right?
It-
So you're dividing by 1 almost
Yeah.
on these expressions. So if you wanted to use a mass fraction, right, it really would just kind of shift these by a constant amount. It wouldn't really change the shape of the curves.
Not much, maybe here a little bit. And so the full reaction network in the code, given by this set of equations, takes into account at least this many reactions between the nuclides. So what we're going to do is compare the full evolution to nuclear statistical equilibrium, and we're going to analyze when these things break off from each other. And then the second exercise is to do NP equilibrium. This sets the ratio of neutrons to protons. If I start at very high temperatures, so tens of MeV, we assume that the number of neutrons and protons is the relative fraction of those each equal to a half. Then at between 10 MeV and 1 MeV, we have these Urca processes, basically charge current reactions for neutrino capture and lepton capture and their inverse reactions. And if we assume the equilibrium condition that the chemical potentials are equal, then that sets the ratio by exponential dependence on the mass difference between the neutron and the proton, which is 1.3 MeV. So what you'll do here is, if you were to solve the complete equation, you would get this curve here. This is nuclear statistical equilibrium for the proton fraction, which by charge conservation is equal to the electron fraction. So that's what we'll do this afternoon, and like I said, we've prepared notes to help you through that. So thanks. I hope you ask lots of questions. Or I hope you ask no questions.
Just one question.
Yes.
So for the nuclear statistical equilibrium with the chemical potentials and stuff, like the neutrinos and stuff, those have negligible chemical potentials, so we don't care about those. Is that why?
That's right. Yeah, so the number density is very small. Number density is an odd function of the chemical potential. The chemical potential of the species and its antiparticle are opposite. So I think I said that backwards. So the chemical potential is an odd function of the number density. And so if the number density is small or 0, then the chemical potential is 0. Yes?
So you said that a problem with a lot of reaction networks now is that unitarity is not conserved or isn't implemented, right?
Yeah, I'm going to talk about that tomorrow a lot.
Okay. So you talked about how that shows up and stuff?
Definitely. Yeah, there are two examples that we've worked on recently that show that in pretty strong relief. In fact, one of them was a reaction that Carla had in her talk. It's alpha capture on carbon-13. Recently, we've revisited that accepted cross-section and found that unitarity is essential to understanding what the correct reaction cross-section is.